Okay, I'm going to pick up on using linear and binary searches. Linear search starts with the first element and looks at each element one at a time to see if it is the correct element, and if it is, return the location. I'm going to ask that you continue to read all of this, but here's a test tip that I found that was important. The first element in a list is 1, and the last element in a list is equal to the length of the list. This may be different from the language that you learned. Pseudocode for a linear search looks as follows. Ask a person what they are trying to find. Store this in a variable called target. Create and store 0 in a variable called index. And while index is less than the length of the list, add 1 to index. Compare it to the target. If the target is equal to the element, return the index. Otherwise, return -1. Now, a binary search assumes that a list is already in order and takes advantage of it. For each division by 2, if the result is not an integer, you can assume that it's rounded up. The procedure that manages this is not shown. This is called roundup. Here's the pseudocode, though, for the binary search, which I talked about in the last video. So you're asking the person what you want to find. You call it a target. You create variables low, high, and middle. Low is the first element. High is the last element. And what the middle is the middle element in the list. Now, this part of the algorithm, you're checking first to verify that low is less than or equal to high to make sure that there's been no crossover. But essentially, you want to know if what's in the middle is less than your target. That means it's on the left side of the list. That means we're throwing out the right side of the list and we reset low equal to middle. And if that's not true, then that must mean my item could be in the top part of the list, which then we would throw away the bottom half. So if it's not in the lower half and it's not in the upper half, then it must be in the middle. So I'm going to suggest to you that you take a look at some of the examples that you might have. Continuing on for algorithms, I'm going to skip a couple pages. I'm going to let you go through this, and now I'm going to come to C. Usually in an ordered set, binary search is faster than a linear search, so this is pretty important. On average, if the set has 16 elements, it would take 4 loops to find the target. Each loop eliminates half the set, so 16 elements would go down to 8, then 8 would go down to 4, 4 would go down to 2, and then you should finally find it in the 4th loop. So in terms of efficiency, you're going to find that the binary searches are more efficiency. They take less time. Notice these numbers are less than the numbers found for linear search. As the size of our list grows, you can see that the difference becomes even more significant. Okay, wrapping up my video on algorithms, I'm going to switch to D. Optimization problems find the best, find the smallest, often cannot be solved in reasonable time, but the approximations to the best solution can be solved in a reasonable time. If an algorithm is analyzed and it is determined that the number of comparisons can be modeled using a polynomial function or better, this means that the algorithm will run in reasonable time. Now, down here at the bottom describes linear efficiency, so I want you to take a look at that. That would be referred to as O to the n. Quadratic efficiency, they give you an example where O to the n might be n squared. An example of efficiency that is better than polynomial is called logarithmic. So these are going to give you lower numbers, and lower is better. Logarithmic functions require less comparisons than a linear function for a large data set, and we did see that here on this other page. A binary search has logarithmic efficiency. Binary search has efficiency log base 2 of n, since it means that it requires fewer comparisons than even a linear search. It runs in a reasonable time. And finally, based on some of those first definitions that we saw, make sure you can explain the difference between decidable and undecidable problems. An undecidable problem may have a solution for some situations, but not all. A decidable problem has a solution for all situations. Therefore, a decidable problem may or may not run in reasonable time, but it is solvable. You'll get an answer. An undecidable problem may or may not run in reasonable time, and it may or may not be solvable.